So now we are going to learn about bootstrap confidence intervals, and first of all we will cover the non-parametric case for the population mean. So we will be looking at confidence interval for the population mean, then we will also look at for the difference of the two means and the ratio of the two variances. Okay. Likewise, we will also see for the parametric case. So first of all, let us begin with your confidence interval for population mean in case of non-parametric case. So here we do not know that the sample is coming from which distribution. We do not have any idea about the population from which the sample has been taken. So let us first of all import the necessary libraries. So we will be importing NumPy, and we will also be importing matplotlib, because we will be making different graphs and plots, pyplot as plt. So now suppose we take a sample data, and for this we use np.array. So we are going to create an array for this data set. So suppose the values are 23, 28, 32, 37, 44, 49. So these are just some random chosen numbers. You can change these and work accordingly. So basically here we have created an array of your sample data. Next, let us specify how many bootstrap samples do you need. Suppose we need 10,000 bootstrap samples. So it will set the number of bootstraps to 10,000. This is the number of times the resampling process will be repeated. Now let us also specify the resamples, number of resamples. Let it be whatever is the length of this data that we have over here. So you can see you have 10 observations. So here what it will do is, here we are specifying n underscore resamples as the length of this data. Okay, so it will set the number of resamples in each bootstrap sample to the length of the original data array. So it will be taking 10,000 samples from here, and each will be of size 10, because here also you have this 10 observations. 3, 4, 5, 6, 7, 8, 9, 10. Now let us initialize an array to store, initialize an array to store the resampled means. Okay, so for this let us write bootstrap underscore means as np dot zeros n. So what we are doing over here, this step over here basically initializes an array of zeros, and what will be the length of that array? It will be of size 10,000. This will store the mean of each resampled data set. So initially we have an array of zeros only. Okay, and it will keep on getting updated every time a bootstrap sample is taken. Now let us perform bootstrap resampling. So we will initiate a for loop for I in range this. Okay, so this for loop will iterate 10,000 times, because n over here is 10,000, and for each bootstrap sample we are going to generate a random sample with replacement. So we will write resample is equal to np dot random dot choice, because we are doing resampling with replacement. So data, and it will be of size what we have defined over here, n resamples, and we are writing replace is equal to true. So what it does is, it will randomly select these many size of the sample points from the original data set that you have over here, and it will be done with replacement. So some data points can be chosen multiple times. So from here itself the data is this, right? We have whatever we have taken, this is the sample data, and from here 10,000 samples will be taken, and each time it will be of length 10, and obviously we know that it will be with replacement. So there can be some data points that can be repeated in a given sample. So probably you can think of it in the way that 23 might appear twice, or maybe 28 appears 3 times. Now you will calculate the mean of the resample data. So for this we will write bootstrap underscore means. This will be np.mean of the resample. Okay, so it will calculate the mean of the resample data that we have obtained here, and it will be stored in this array. We have initially so basically this is initialized as zeros. So here basically you can see that you have an array of zeros, and now it is getting updated every time the bootstrap mean is calculated. Okay. Now what we will do? We will sort these bootstrap means in ascending order, because we need to find the confidence interval. So we need to arrange them in an ascending order. So we can write sorted underscore means as np.sort. So here we are using this function from NumPy libraries, bootstrap underscore means. So here this step would sort the bootstrap means in ascending order, and this will be now used for calculating the confidence intervals. How you will calculate the confidence interval is, suppose if you want to find out the 95% confidence interval, so we need the lower and the upper bound. So lower bound would be sorted means that you have defined above, and here we will be taking the integer value 0.025 times n. So what we are doing over here, we basically want 95% confidence interval. So it means 1 minus alpha is 0.95, alpha is 0.05. Now when we are considering two-sided interval, it means that if you consider the lower bound, it would be the area to the right of it would be alpha by 2, so it will be 0.025. So when we write 0.025 of n, so it will calculate 2.5% of this, of 10,000, right? Because we have arranged it in ascending order. From bottom, it will go to the point below which 2.5% of the bootstrap sample means fall. So it will provide the lower limit for where the true population mean might lie with 95% confidence. And here if you see why we have written this integer, basically we want the value at the index that represents a 2.5 fifth percentile in the sorted bootstrap means, right? So we want the integer part. So this will convert this function over here, this integer function over here converts the number to an integer, which is basically necessary because your array indices must be integers. Likewise, you can have the upper bound. So what will happen here? So the lower bound will be 0.025 and this one would be 0.975, because 97.5% of the points would be below this from the upper bound. So alpha by 2 is above that, right, to the right of it, and 1 minus alpha by 2 would be below that. So basically it means that it would be 0.975 of n. So 97.5% of n would be, and its integer part will be taken and it will be stored in your upper bound. So you have obtained the bounds. Now we can print the confidence interval. So print that 95% confidence interval for population mean. So we need the lower bound. So we can use this lower bound. So first it will evaluate whatever is the value obtained and stored in lower bound, and we will specify the format over here. That is, we are going to consider up to 2 decimal places only. Likewise, it will also print the upper bound. Okay, so let us run this. Sorry, here it should be, oh sorry, this round bracket is missing over here. Yeah, so 95% confidence interval for population mean. You will have the lower bound comes out as 37.30 and the upper bound comes as 58.50. So you see that even when you were unaware that your sample is coming from which data, which distribution, you do not have any idea about that, still you are able to find out the 95% confidence interval for the population mean. Now suppose you want to plot the histogram for this so that visually you can see what is happening over here. Plot the histogram. So we have used it earlier also, right? So we can just simply write the commands. Plot.hist. We want to plot these sorted means, and suppose you want 50 bins and the color can be blue, and your transparency level we are fixing it as 0.6. You can label the x-axis, and likewise you can label your y-axis also. So on the y-axis we can write frequency, and the title of this could be bootstrap distribution of population mean. Now suppose you want to make a vertical line at the lower and the upper bounds. You also want to display these bounds that you have obtained. So for that we will use plot.axv line. Okay, so it will basically draw a vertical line, and where do we want that? We want it at lower bound. We can specify the color of that line. Color can be red. Line style can be a dashed line, so we can write this, and we can give it a label as lower bound. Likewise, you can draw a vertical line again at your upper bound. So maybe we can change the color over here so that you can distinguish. And upper bound. Yes, so this is how it looks. So you also have the overall means, because for each bootstrap sample you calculated the mean and you have plotted the means over here. This is the histogram of the sorted means, And here you can see your lower bound and upper bounds are also visible, which basically covers 95% of your data set over here. So you can say that, so 95% confident that your population mean would fall between 37.30 to 58.50. So this was the bootstrap confidence interval for population mean. Likewise, you can have two different populations and you might be interested in the difference of the two population means. Okay, so we will be now writing the code for confidence interval for difference of two population means. So if you can recall, we have done a similar thing when we were drawing the samples from normal population. So here we are not assuming any distribution and we are just trying to find out what will be the confidence interval in those cases. So again, we will be importing numpy as np. Although you have already imported it, I am rewriting it so that you know from where to start whenever you are writing any code. matplotlib dot pyplot as plt. Okay, so we know the functions of these two, right? So numpy is used for basically your arrays and matrices, and it can perform various mathematical functions also on these arrays. And matplotlib library is used for plotting the functions, right? So since here you have made this histogram, so matplotlib was used here. So after this, let us write what is the sample data for the two groups. So let me write for group 1 np.array. So I can use the same one for first data set, first population, and you can simply rewrite this. And for the other group, group 2 can be, suppose it is 18, 25, 30, 40, 45, 50, 57, 62, 67, 72. Okay. So obviously here I am just considering these of size 10 only. If you want to increase it, you can do that and check your results. So these basically group 1 and group 2, these are your numpy arrays containing sample data for the two different groups. After this, we would again specify the number of bootstrap samples that we will be taking. So let that be 10,000. And the number of resamples, this would be same as the length of the data set. So group 1, even for if you write for group 1, that will be same for group 2 also. Now we are going to initialize an array as we have done earlier. So here you would see the similarity between the first code that we have written for single population mean, and here we are writing for the two population means. So everywhere we have to be dealing with two groups, right? So here we have stored this data in two different variables. Likewise, we would be generating samples also again for 2 times. So let us initialize this. So bootstrap underscore differences would be storing np dot zeros. Okay, so here it will initialize an array of zeros. Next, for performing bootstrap resampling for the differences, we will initiate a for loop for I in range n. Okay, so this will iterate 10,000 times, and for each resampling process, what it will do, it will generate random sample with replacement for both the groups. So suppose for the first one, let me write resample 1. So np.random.choice. Okay, so here we can write for the first group, and size would be again, what is your n resamples over here? That is size 10, and replace is equal to true, means that we are going to be doing sampling with replacement. Likewise, we can define for your second sample also. So here it will be resample 2, you will have group 2. Okay, so here you are basically redrawing the random samples with replacement from these two sample data sets. Okay, and the size of each sample would be 10 only. Now we would also calculate the mean for each of these. So mean would be mean 1 basically. For this we will calculate numpy's, so we will use numpy's mean function. So resample 1, and likewise you can obtain for the second one also. Resample 2. Now you can find out the difference between these two means, right? So sample mean 1 minus sample mean 2. So you would write bootstrap so mean 1 minus mean 2. So the means of these resample data sets which we have obtained over here, their corresponding differences will be taken for each bootstrap sample, and it will be stored in this array that we have initialized. Okay, once you have obtained this array, finally we are going to sort it out. Sorted differences will be np.sort and bootstrap differences. Right, let me just again, you will find the lower and the upper bound. So I will just use it from here. We need the print command also. So lower bound will be, so here we have stored it in sorted differences. So let me write differences. Again, differences. Okay. So we have found out 95% confidence interval. So at alpha by 2 and 1 minus alpha by 2. So this first one covers 2.5% of the total number of samples, and here it would be 97.5. So it is basically the point below which 2.5% of the bootstrap sample means fall, and this one would be the point below which 97.5% of the bootstrap sample means would fall. Then obviously we will give these commands. So here it will be for difference of population means. So you can see that it starts from minus 14, the lower bound is minus 14, and here it is 16, upper bound is 16. Now if you want to visualize it using the histogram, we can use that. So let us reuse this one. So let me just write the command over here itself. So here it will be sorted differences. So bins and color we can keep same. So bootstrap differences. Frequency is there. Bootstrap difference. Bootstrap distribution of difference of population means. Again, rest of the things can remain the same. Yeah. you can see that these are the histograms of the difference of the two means. This is your lower bound, which is denoted by red line, and here you have the upper bound, which is green. Okay, so minus 14 to 16.5, so 95%. Over here you can see that your population mean, we are 95% confident that the difference of the population mean in this case would fall between these two endpoints, which is also evident from the histogram itself, because you can see that 95% is covered. Only this outside region that you have, that accounts for 5% overall, so it would be 2.5% on each side. Okay, because it is almost symmetric in this case. So we are done with the bootstrap confidence interval for population mean and for difference of population means. Likewise, you can write for variance also. So here I will be writing the code for the ratio of the two population variance. Obviously, you can write for the single population also. So let me just mention confidence interval for ratio of two population variances. Again, we have seen this when we were dealing with the normal distribution. So we have seen earlier also that if you have two normal populations and from there you draw the random samples, so how you can find the confidence interval for the ratio of the two population variances. So here also we are going to do the same thing. The major difference over here is that we do not assume that the two populations are normally distributed. So we will be importing numpy as NP, and we will also import your matplotlib as PLT. So sample data. So we can take the same data set that we have obtained over here. So I see most of the things here would remain same, so we can just use that. So sample data is same. Again, we would be taking 10,000 bootstrap samples, and size of each sample here we will be considering as same as the size of the first group, length of the first group, which is basically 10. We will also be initializing an array. So here we would use bootstrap.ratios. So this is an array of zeros, and the length of that array would be same as 10,000. Now you can perform your bootstrap sampling for ratios. So as you know, we will be initiating a for loop for I in range this 10,000. For each bootstrap sample, we are going to take a sample, so resample with replacement, so np dot random dot choice. So here first argument would be the group that you have, then size would be the same as this one, resamples that you have written over here, and then you will write replace true, which basically means that we will be doing sampling with replacement. Likewise, we can write for the second sample also. So resample 2, and here we will be writing this. So for the second group also, you have generated random samples. Now you have to calculate the variances. Okay, so in the previous one we calculated the means. So variance 1 would be the sample variance np.var for the first sample, resample 1, and dd of is 1, which basically means we are working with the sample variance. Likewise, we can write for the second one, it would be np.var the second one, dd of is equal to 1 again. Now we can calculate the ratio and store it. So maybe we can write here only bootstrap so variance 1 divided by variance 2. Once you have obtained this, you have obtained an array of this bootstrap ratios. We can sort them in ascending order. Sorted ratios would be obtained using this np.sort function, and for here we will just use this bootstrap. Okay, then again you can find the lower and the upper bound. So lower bound would be sorted underscore ratios here, and again we will be considering the integer part of this 0.025. That is 2.5 of n, 2.5% of n. Okay, likewise you can write the upper bound also. So here it would be 0.975. So again we are finding 95% confidence interval, sorry. We can now print and write the code for the histogram. So that basically is same. So we can just reuse it from here. So here it would be for ratio of population variance. So you can find that the lower bound is 0.35. That is S1 square over S2 square. So ratio of 2 population variance, it means that we are 95% confident that sigma 1 square over sigma 2 square would fall between these two endpoints. Okay. We can again find the histogram. We can make the histogram over here. So for that we would just use the same command. So here it will be row sorted ratios. Okay, because we have stored the bootstrap ratios arranged in ascending order in this. Again here it would be bootstrap ratios, bootstrap distribution of ratio of population variances. The rest of the things would remain the same. So you can see that variance ratio of 2 population variance is there, and so it is skewed, right skewed. So if you can recall in your normal distribution case also, it is skewed because there we have your chi-square distribution, starts from 0 to infinity, and it is right skewed. So here also sample variances, if you are considering, even when you do not know the original population, still you can find out the 95% confidence interval, and you can see that from these lines red and green, which is the lower and the upper bound, it can be seen how 95% is lying between these two endpoints. So this is how you can find out the confidence interval if you are working with population means, or you are working with population variances, or the ratio of the two variances, or any other statistic in which you are interested.